Today, we are discussing about inference procedures for threshold parameters. We can start our discussion by talking about threshold parameters. Threshold parameters are occasionally introduced to lifetime distribution models. It is denoted by gamma, which is greater than or equal to 0. Threshold parameters indicates a time gamma in which an individual cannot die. That is, in that time, an individual can never occupy its lifetime. In every distribution, we can include threshold parameters by replacing lifetime t by t transpose is equal to t minus gamma with t greater than or equal to 0. Threshold parameters can be estimated by maximizing the correlation function from the plot of the distribution. It defines the lowest possible value in a distribution. Now, we are entering to a generalization of inference procedure for threshold parameters. If a model has a probability density function of the form f of t theta gamma is equal to f naught of t minus gamma theta where t greater than or equal to gamma, ti comma delta I is a censored random sample of lifetimes, then the parameter gamma must be less than or equal to ti, where ti is the minimum of all lifetimes. Since we require that the PDF must be greater than or equal to 0 and the survival function must be in between 0 and 1, then the likelihood function is given by the equation 2. For some models, this likelihood function is unbounded. This behavior can be avoided if there is a finite degree of precision within which a continuous variate can be measured. Replace the values for the PDF f of ti in the likelihood function with equation 3. Here, capital gamma represents the precision of measurements. If gamma is small, it very close to 2 gamma f of ti and there is no need for this adjustment. But ti keeps the likelihood finite and restricts gamma to be less than or equal to ti minus gamma. An alternate approach is to leave the restriction gamma less than or equal to ti but replace f of ti in the likelihood function with f of ti plus gamma minus f of ti. The estimation of gamma is also generally non-regular for certain values of theta in models such as Weibull. To estimate theta, examine the fit of models with gamma assumed as known. Let us consider the observations Si is equal to Ti minus gamma for the lifetime distribution f naught of Si theta where the estimation is regular. The plausible values, that is, the trustable values for gamma can be determined from the profile likelihood function given in equation 4. Here, theta cap of gamma is the maximum likelihood estimate of theta when gamma is known. A plot of profile likelihood function shows plausible values for gamma. It is possible to modify the profile likelihood function by reference to a chi-square distribution with 1 degree of freedom for an associated likelihood ratio statistic. But the unboundedness of the actual likelihood function manifests itself in the profile likelihood function. If we replace the PDF with either capital F of Ti plus gamma, theta gamma, minus capital F of Ti minus gamma, theta gamma, or with F of Ti plus gamma, theta gamma, minus F of Ti, theta gamma, then the likelihood function and profile likelihood function will be bounded. Let us consider an example of 3-parameter Weibull distribution. The density function of the distribution is given in equation 5 and the likelihood function for censored random samples are given in equation 6. Then we have two conditions. One is beta less than 1 and another is beta greater than or equal to 1. If we consider the first condition, that is, if beta less than 1, the likelihood function tends to infinity as gamma tends to Ti. Thus, the likelihood will become unbounded. Then, a solution to likelihood equations does not produce a global maximum for the likelihood. If we consider the second condition, that is beta greater than or equal to 1, there is also two conditions. The first condition is that with a restriction beta greater than or equal to 1, the likelihood function is bounded and it may have a local maximum at a point alpha cap, beta cap, gamma cap with alpha cap greater than 0, beta cap greater than 1 and gamma cap less than Ti. The second condition is that if there is no local maximum, the likelihood is maximized over the region with alpha cap greater than 0, beta cap greater than or equal to 1 and gamma cap less than or equal to Ti by gamma cap is equal to Ti, beta cap is equal to 1 and alpha cap is equal to summation I from 1 to n Ti minus gamma cap divided by R. This can also give the global maximum of likelihood when a local maximum exists. But these estimated calculated by equation A, the methods A and B are same. To obtain the MLE and values for gamma, we compute the profile log likelihood function just like in equation 8. Here, alpha cap of gamma and beta cap of gamma are the maximum likelihood estimates of alpha and beta with gamma held fixed. These estimates are found by treating the values of Si equal to Ti minus gamma as a censored sample from the two-parameter Weibull distribution. A graph of profile likelihood function gives plausible values of gamma under the condition gamma less than or equal to Ti. When the maximum likelihood estimates of alpha cap, beta cap, gamma cap has been obtained, the log relative profile likelihood or the corresponding likelihood ratio statistic can be calculated. Asymptotic theory shows that if beta greater than 2, then capital gamma of small gamma naught has limiting chi-square distribution with 1 degrees of freedom when gamma greater than 0. If beta less than 2, then the limiting distribution of gamma is not chi-square with 1 degrees of freedom. If beta is equal to 1, we have two-parameter Weibull distribution and gamma is asymptotically chi-square distribution with 2 degrees of freedom. Here we are given some characteristics of threshold parameters. 1. Interval estimation and tests about distribution characteristics are best carried out with gamma treated as known. The sensitivity of inferences to variation in gamma can be examined. Point estimates and confidence interval for alpha and beta often vary widely as gamma is varied. This reflects the fact that the likelihood function is flat near the MLE and that the MLEs are highly correlated. The data are informative only about certain functions of alpha, beta and gamma and not the individual parameters. Estimates of the quantile TP are often quite stable as gamma varies, and it would be then reasonable to quote confidence limits for TP with gamma assumed to be equal to gamma cap.